In this lesson, we're going to talk about the gaseous state of matter and Boyle's law. First, let's talk about what makes gases different from solids and liquids. Take a look at this picture. If the orange spheres represent the particles in a substance, notice that the gaseous substance has particles not touching each other at all, whereas the liquid and solid do have particles touching each other. The solid state has the particles in rigid formation, locked together as if they're in like a crystal formation, whereas the liquid particles are touching each other, but they're slip sliding past each other. Also, notice that in the gaseous state, we need a lid to the container, whereas the liquid and solid containers can be open. The gaseous state needs to have a closed top, otherwise the particles would escape to the air around it. For every substance without exception, including water, remember water was unique in that its liquid state was more dense than its solid state. But for every substance, gases are by far the least dense of the three common states of matter. They exist at the highest temperature ranges of any of these common states of matter. And they have what's called indefinite shape and indefinite volume. I want to talk about that in just a moment. Consider water, the substance we're probably most familiar with. The solid state of water exists at temperatures below 0 degrees Celsius. The liquid range of temperatures for water goes from 0 degrees Celsius up to 100. And then the gaseous state exists at temperatures above 100. So when we say gases exist at the highest temperatures, that means for any given substance, if you start in the solid state and you keep adding energy without stopping, first you'll melt it to become a liquid, and then you'll eventually boil it to become a gas. And at some point, and there is a fourth state of matter called plasma that exists at only extremely high pressures and high temperatures, the kinds of pressures and temperatures we don't see on Earth. Now let's talk about indefinite shape and volume. When I pour my coffee into my coffee mug, the liquid takes the shape of the mug. If I pour that coffee into a different shaped mug, maybe a smaller one, it'll take the shape of the smaller mug. It might even overfill it. Liquids take the shape of their container. They themselves have indefinite shape. But whether I put my coffee in a small mug or a bigger mug, it has a certain volume. And I could measure that volume. If the container had gradations on the side of it, I could actually measure it. With gases, they both have an indefinite shape. They'll take the shape of whatever container they're in, but they also will expand to fill it, meaning you can take the air particles in, let's say, a scuba tank, which are compressed, highly compressed, and you can let them out into a room, and they would take not only the shape of the room, but the volume of the room. They'll expand to fit any container. Liquids don't do that, and solids certainly don't do that. So the gaseous state is certainly unique. Because gases exist at the highest temperature range for any of the common states of matter, we can say that they are the fastest moving particles. Recall maybe from physics that higher kinetic energy means faster movement, provided that the mass isn't changing. And that is the case, that the mass of the particles doesn't change with differing temperatures, only the velocity does. So we've got widely spaced apart, fast moving, and high energy particles in the gaseous state. Here's a picture of a beaker that is under a Bunsen burner. Now, if you keep heating that beaker of water, it'll start to boil. And if you continuously heat that for a long, long time, the whole sample will boil away. The reason for that is that as you input more and more energy into the particles, the average velocity of a particle in the sample is going to increase. And if the average velocity is faster than the strength of the intermolecular forces holding the particles in the liquid state, then it will escape. It'll achieve escape velocity and it will enter the gaseous state. There's a whole theory around this, and it's important conceptually for understanding gases. It's called kinetic molecular theory. Kinetic meaning motion, molecular meaning we're talking about particles, and theory meaning it's a way of explaining phenomena in science. It has 4 parts. First, gases are collections of particles in constant motion. They will eventually collide with each other. And when they do so, we're going to assume that those collisions are billiard ball-like collisions. They'll bounce right off each other and not necessarily exert attractive forces on each other. They also will collide with the walls of their container. We'll talk about that in a moment. That's going to be an important piece of this. 2, we assume no attractions or repulsions between particles. Collisions are like billiard balls. 3, there's a lot of space between the particles compared to the size of the particles themselves. This is kind of hard to visualize. Since we're so used to dealing with solids and liquids, most gases that we encounter are invisible to our eyes. We're just not used to thinking of particles in the gaseous state. So here's an example. I don't know if any of you have ever traveled to Montana, but it's a beautiful place. It's a big, big, wide open state. They call it Big Sky Country because there are these huge expanses. You can see hundreds of miles in any direction. And that's the kind of wide open spaces you don't see in Chicago. Well, the population of Montana is fairly small, very small, in fact, for its land area. If you were to talk about population density, it's extremely low in Montana. You could easily double, triple, even quadruple its population, and it wouldn't feel it would not feel much more crowded than it is right now. So there's very few people per square mile. It's kind of like that with gases. There's a lot of space in most situations that we encounter between the particles, such that you could easily double, triple, or even quadruple the number of particles in a sample, and you wouldn't appreciably change the density. The 4th part of kinetic molecular theory, faster particles are hotter. Just faster is hotter particles are faster is the easiest way to put it. The speed that the particles move increases with increasing temperature. Now, let's talk about those collisions, not necessarily with the gas particles, but with the walls of their container. Every particle is moving fast, and even if the mass of a given molecule might not be all that much, when you have billions and billions of them in a sample, and they're all colliding with the walls of their container or with each other on the level of thousands at a given instant, there's enough pressure due to those collisions that you can measure it. Every single gas particle has a momentum. The momentum, when it's transferred to the walls of their container, exerts a pressure, and it's proportionate to both the number of particles and the speed with which they're moving. We'll see that in some of our gas laws coming up shortly. The force imparted by billions of molecular collisions adds up to the total gas pressure. Here's a rather intuitive question. You don't need to calculate. I think you're just going to kind of get a sense of this. I have 2 jars of a gas sample. In one of the jars, there's twice as many particles, but the jars are held at the same volume and the same temperature. In which jar would there be more pressure? Most of us would say, well, there'd be higher pressure in the jar on the right where there are more particles. And that's due to the number of collisions happening with the walls of the container at any given instant. Here's a physics definition. I know this certainly isn't a physics class, but physics does help us every once in a while. When we talk about pressure, we're talking about the force per unit area of molecules bouncing off the walls of their container. If you have more molecules, you're going to have more molecules bouncing per unit area. So pressure is proportional to the number of molecules. And if the particles are moving faster, that is, if they're hotter, they're going to strike the walls of their container more forcefully, which also increases the pressure. So pressure is proportional to, meaning it goes up when the following go up: the number of molecules and the velocity or speed of those molecules. We don't often think about it, but we here on Earth have experienced pressure at all times. We're so used to it, we don't even consider it. But Earth's atmosphere is a mixture of several types of gas molecules which bounce off everything in it, including ourselves. In fact, you wouldn't be able to breathe right now if the gas molecules that make up our atmosphere weren't exerting a pressure on your lungs. Most of the atmosphere, as you may know, is nitrogen. A pretty appreciable amount is oxygen. A small amount is argon, and there's teeny tiny amounts of other gases. So it's a mixture of all of those that add up to the pressure that enables you and I to breathe. Back in the 1700s, some very clever scientists invented a scientific instrument that enabled us to measure atmospheric pressure. It's called a barometer. And the way it works is you take a dish of mercury, and the reason we choose mercury is because it's the densest liquid that we know of on Earth. You could use other liquids, but the container, the instrument would have to be much, much bigger than if it were the liquid were mercury, something other than mercury. So take a dish with that's completely filled and a tube that has mercury in it, invert the tube upside down in the dish, and then let gravity pull the mercury downwards just a little bit in the tube. The space at the top of the tube that's been inverted is a vacuum. There's no air in there. That's just the weight of the mercury falling downwards due to gravity has created that space at the top. And then you might say, well, what's holding the mercury up? Why is it even at any height above the level of the mercury in the dish? Well, that's balanced by the atmospheric pressure. The weight of the atmosphere bouncing off the surface of the mercury in the dish is what's pushing the mercury up in the tube. And as it turns out, there's a certain height that the mercury at sea level is always at. It's 760 millimeters of height. And since the chemical symbol for mercury is Hg, one of the most common units for pressure is millimeters of mercury, or mmHg. Other units that you do need to be familiar with are atmospheres and kilopascals. Let's set an equation that allows us to go between these different ones. At sea level, the atmospheric pressure is 1 atmosphere, which is equivalent to 760 millimeters of mercury, which is also equivalent to 101.3 kilopascals. Now let's turn our attention to one of the most important of the gas laws or gas breakthroughs in understanding gases that was put forth by Robert Boyle, a British scientist. Consider these 3 containers. We've got a thermometer in the top, we've got a pressure gauge in the top, and they're showing the pressures and temperatures down below each container. By the way, where you see the K, that stands for degrees Kelvin. We're going to talk more about that in the next lesson. But in the container on the left, we have 1 atmosphere of pressure. The volume of the container is 1 liter. In the middle container, half as much volume, twice the pressure. And in the container at the right, 1/4 as much volume as the one on the left, and 4 times as much pressure. The temperature is the same throughout. And if you bothered to count up the number of red dots in each of these containers, you would see that there's 14. Every single one of these containers has the same number of particles. So they're trying to indicate that the number of moles of particles isn't changing. Robert Boyle noticed that with lower volume, gas molecules must bump into their container more frequently, exerting greater pressure. We kind of had a sense of that with that comparison of the picture of the 2 jars earlier. More frequent collisions will result in greater pressure. But what Boyle did is he said, okay, I'm going to freeze the number of particles and just shrink the volume. He made a graph of pressure against volume, and it looked like a graph of y equals 1 over x. So if you think back to math class, y equals 1 over x proceeds from the upper left of quadrant 1 to the lower right, and it is a curvy line. It's not a straight line. It goes from upper left to lower right with an asymptotic approach as you go to the axes. Putting all this together, Boyle's law looks like this. If you take the pressure times the volume of a gas initially, the subscript 1 in the formula refers to initial conditions, that will be equal to the pressure times the volume at the end. The subscript 2 refer to final conditions. In other words, pressure and volume are inversely related. As one goes up, the other is going down. Here's another graph of pressure versus volume. This one's a little bit bigger. I kind of like this one either. Boyle said, hey, the pressure times the volume of a given gas sample is going to be a constant. So whether it's under condition 1 or condition 2, those two, the product of pressure and volume will be equal. Let's finish up today with some mathematical expressions of Boyle's law. Let's say we've got 2 liters of oxygen gas at 1 atmosphere that's going to be pressurized up to 4 atmospheres. What would be the new volume? First of all, do you think the volume would go up or go down? If we know that pressure and volume are inversely related, if you increase the pressure, the volume goes down. Okay, how much? Let's use the formula. P1 times V1. They tell us we've got 2 liters of gas, that's V1. It's at 1 atmosphere of pressure, that's P1. We'll multiply those together, so 2 times 1 is 2. It's pressurized to 4 atmospheres, so that's our P2. What's V2? Well, it would be 2 times 1 equals 4 times X. We'll take 2 times 1 and divide that by 4, and we get a new volume of 0.5, or half of a liter. That one was easy mathematically. Let's try one a little bit harder, and I'm going to ask you to remember how to convert between pressure units. 500 milliliters of a gas at 1 atmosphere later experiences a pressure of 600 millimeters of mercury. What will be the new volume? Notice they give us a pressure unit in milliliters. That is a-okay to leave it in milliliters. But the pressure units, there's 2 of them. One of them was given to us in atmosphere, and the other one was given to us in millimeters of mercury. We have to convert one of them into the other. And it doesn't matter which one you convert into the other. They just need to be in the same unit. I'm going to convert 600 millimeters of mercury into atmospheres. And the way I do that is I'm going to remember that at sea level, the atmospheric pressure is 1 atmosphere, which is equivalent to 760 millimeters of mercury. So if I want to convert from millimeters of mercury into atmospheres, I'm going to take the 600 millimeters of mercury and divide it by 760. That gives me a pressure of approximately 0.79 atmospheres. Having done that conversion, we're ready to apply Boyle's law. 500 milliliters times 1 atmosphere of pressure, that's P1 times V1. And we're going to set that equal to 0.79 atmospheres times the new volume, which is unknown. Let's call that X. Okay, so 500 times 1 divided by 0.79. That gives us 633 milliliters. In the homework, we're going to ask you to apply Boyle's law to some new situations. Good luck.